Right, in all these questions of estimation, there is no right answer. Because we're all guessing, we should be able to come to sort of like a ballpark figure. And I think if you're, 5 times too low or 5 times too high, that's fine. That's fine. As long as your method is okay, you should be all right. So, estimate the electrical power of a small town. Well, of course, the small town, you could end up with a town like Taunton, which is, I suppose, a medium town. That's about 80,000, but 20,000 is roughly a small town. Now, this assumes you do geography, you know what small towns are. So you could have anything from, say, I don't know, 5,000, maybe up to 100,000. So you could see the range we've got there already. So if you say a small town of 20,000 people, then you have to consider, well, what am I using electricity for? Well, there's some things that are on all the time. So on all the time, for example, are things like fridges and freezers and there's little red lights that show that something's on standby. Well, they do drain a bit of power. I mean, fridges are probably averaging around, say, 100 watts all the time, and they're constantly on. Then you have some things that are rarely on but use a lot of power. So they're things such as say kettles, for example, would be there, and a kettle, for example, uses 2,000 watts. Things like an oven, for example, would use something like 7,000 watts or 7 kW, and things like a shower, electric shower, will be the same, roughly 7 kilowatts. Now, of course, they're not on all the time. There are some things, of course, that are on there for a fair bit of time. Things like your TV and your PC. Well, they've got a rate around 200 watts. You just need to be familiarised with things. And the more you do physics, the more you get a feel for the power of these things. So I think it's reasonable to say that the average human being probably needs about 1,000 watts or 1,000 joules per hour. That is the power that you need in order to keep things going in your house. And since there's 20,000 residents, you do 1,000 times 20,000, and then that will give you the figure of 20 million watts, which is probably best expressed as 20 megawatts. Okay, next one. That's your final answer. Estimate the force on your legs if you jumped off a 2-meter high wall and landed on your feet. Okay, right. So if you jump down, say, 2 meters, you'll be going at a sort of high speed, wouldn't you? If you're on the ground, by the way, and stood there by yourself, well, your weight will be pulling down on the ground. There's your legs. And the weight of an average human being is something like 700 newtons. So when you drop down, obviously as you hit the ground, you're going to slow down. So what sort of speed would you be doing at the bottom? Well, we can use the equation for potential energy equaling kinetic energy. There's loads of ways of doing this. This is one way, so it's a half mv squared. You can quickly get rid of the masses. There you go. If you rearrange this, you get an equation 2gh square root all that will be equal to v. If you rearrange that formula, that is what you get. Then plug in some values. So you've got 2 times acceleration due to gravity is 9.8, but since it's an estimate, you're all right to do 10. And the height, of course, is 2. And that will equal v, by the way, not v squared, it will equal v. When I put that in, I get an answer of 6.3 meters per second. Because it's an estimate, though, I don't need to do 6.3. 6 is good enough. We know it's roughly in the right sort of area. Now, why have we used this? Well, when you hit the bottom down here, for example, the force will be equal to the rate of change of momentum, which is mv minus mu over t. Okay, now your initial velocity, as now considering this bit here, just before you hit it, your initial velocity is 6. Let's assume that the average mass of a human being is, say, something like 70 kilograms. Okay, so 70 times, sorry, I've got this wrong, you know. That's the final velocity, isn't it? That's the final velocity. So it's 70, your final velocity is going to be 0 because you stood still. Take away the initial velocity, which is 70 times 6. That's just before you land. You're going at that velocity. And I reckon the time, when you hit the ground, you don't stop suddenly. You sort of land on your feet and gently slow down. And I reckon that rate of slowing down is probably something like half a second from when your feet first touch the ground to actually you stopping altogether. So when I do 70 times 0, that's nothing. 70 times 6 is 420. And then I have to divide that by 0.5. That tells me the force needed to slow me down is 840 newtons. Combined, the 700 newtons of my weight, I've now got a total force on the ground of roughly 1,500 newtons. It's 1,540, but remember, it's an estimation. So that's what I reckon the answer is, 1,500. You could use another way, which would be v squared equals u squared plus 2as. There's loads of ways of doing it, but I'm happy with this. This seems to be in roughly the right area. And of course, if ever you've jumped down our wall from that height, you'll know that it does feel very heavy. It feels as if your body is twice the weight it normally is, and that's what the answer there is, twice the weight of your normal body. Right, so they say that the beam of the Large Hadron Collider has an energy of 360 meters, and they reckon it's got the same energy as an express train. So let's estimate what the energy of express train is. Well, to work out the energy of express train, you're going to use the kinetic energy equation, a half mv squared. What is the mass of a train? Well, hold on. If we think of a car as having, say, 1,500 kilograms, so just that's a good unit to think. I reckon a carriage probably weighs maybe 20 times that amount. So you've got roughly 30,000 tons. And if you've got 8 carriages there, that's 30,000 kilograms multiplied by 8. That's going to give you a total weight of the train of being something like 240,000 kilograms. So that's the mass of the train, shall we say. So a half times 240,000. The speed of a train, well, if a human can run at, say, at 10 meters per second, think of a sprinter that's roughly 10 meters per second, and that's roughly 20 miles an hour, roughly. So I reckon that express train go at 100 miles an hour, so that's 5 times as big as that. So we're now looking at, say, 50 meters per second, and that 50 has to be squared. And if I put that in my calculator, I'm going to quickly work it out. 24000 times 2,500, which is 50 squared, times 0.5 equals, well, there we go, it's 300 million megajoules. And that, if you notice, is roughly in the same sort of area as this here. Okay, so again, you've just proven it. A QED, I've shown it to be the case. How long would it take to fill a swimming pool from a kitchen tap? Well, again, think about what a swimming pool looks like. You've got roughly a pool that's going to be, should we say, 25 meters long, perhaps. Let's think probably 2 meters deep and say 8 meters wide. So that's 25 times 8 times 2 is going to give me a volume of 400 meters cubed of water. Now, something you just need to know, guys, is that 1 meter cubed is actually 1,000 liters. It's 1,000 liters. So that's therefore going to be 400,000 liters. That is the volume of your swimming pool. And then how quickly does your kitchen tap flow? Well, obviously the examiner doesn't know how quickly everyone's kitchen taps flows. Just come up with a rough idea. And perhaps the idea here is that think about how long it takes to fill a kettle. A kettle's got about 1.5 liters in it, so you can hold it max. How long does it take you to fill it up? I would say it takes about 4 seconds to fill up, say, 1 liter. Okay, to fill up 1 liter. Therefore, that's fine. So therefore, 1 second is going to, well, that's quite, let's leave it like that. 4 seconds equals 1 liter. We've got 400,000 liters. So if I then multiply this by 4, that is the total amount of time it's going to take, which is 1,600,000 seconds. And that's cool. You could leave it like that if you wanted to. You could change that into minutes by dividing by 60, then divide that by 24, which would then, divided by 60, which should give you minutes, then divided by 60, which should give you the number of hours, then divided by 24, which should give you the number of days, okay, which I believe is something like, according to the exam here, 17 days. Okay, that's it. Hope that was useful to you. Again, the thing is, just remember, there's no right answer. It's just that you've thought about it logically. Just get roughly in the right area. If you're 2 to 3 times within the right answer, you've got it done. Okay.